315. 315, please.
Yeah, she got her his diet. I'm suffering one day. Why? Because I ironed diet. Aww, he's reading them all for me.
Does that help?
Oh,
Does that help?
Last time you did that's me.
Although it might make that even brighter.
Oh, I freaked out when I got outside. It hurts.
Okay. Thursday. Let's see, I can't remember. What did we do on Thursday? Oh, that's right. The fundamental theorem of calculus. Now, we need, I mean, it was kind of unfortunate timing, I think. Well, maybe not. But, you know, to hit that and then have 3 days off. So, but let's go back, and we've got some things we want to get written down, and then also dig into some of the specifics of kind of this big idea that we came up with, which of course was that the area function is the antiderivative of the function you're doing the area under. Okay, so that, I mean, over everything we're doing, that is kind of up above all of it, right? That is the overriding theme of all of this. Now, a lot of what we'll get into is some of the details, and of course, we know how that works with derivative. We talk about the derivative is the slope of the tangent line. Sometimes we forget that, but that's the main idea. And then we got into all these applications. We got into the rules for derivatives. We have the chart. Remember when we first did the chart with all its connections between f and f prime and f double prime, very confusing. Once we organized the chart and wrote it out, and then those things all started to come together and kind of make sense. Well, now that we know this antiderivative connection, the area function is like big F, so to speak. All of those chart connections should all still be there, and that's kind of what we were showing on that calculator thing. So we're going to get into that again today. And so just like then, it will probably be a little confusing at times. The notation is kind of tricky. The tendency in this area function stuff is to make it more difficult than it is because the notation seems weird. We have to put that t in there. We can't use x. And stuff like that, and all of a sudden we tend to make it more difficult than it really is. Okay, so that's kind of what we'll be going through today. You'll probably go through that, where there's going to be times where it seems like we're really getting lost in a bunch of different things, but then in the end it kind of comes out, okay, well, yeah, that kind of makes sense, hopefully. Now, I kind of want to compare it back again to the slope function. So when we first started with slope, we said, okay, you got a curve. How can we do slope on a curve? Because we're used to doing slope on a line. You need 2 points. Well, curve, you only know 1 point because the tangent line only touches at 1 point. So we estimated. We picked 2 points close together. We estimated. Matter of fact, we did. It wasn't a real big aha moment like maybe that was hopefully last week, but it kind of was when we did the sine. Remember that when we plotted the slopes of the sine graph? And it was what? Cosine graph. You know, that was kind of cool. But this is basically what we did. But we just named it derivative. It wasn't like, oh, that's a derivative. We just gave it a name. We said that's called the derivative. But what we did is we made it a function. We said, okay, x is where we're at on the x-axis. That's our input. And then the slope at that point is the y value. And then we collected a bunch of those for sine, and we saw that it made the cosine graph. And we said, okay, that's the slope function of sine. And we called that the derivative. We called that f prime. Okay, so we're doing kind of the same thing here. We're wanting to make like a table of values. The problem is, for our x, you can't do area at a point. You have to do area between 2 points. So what we said is we will pick a left endpoint. Now you notice over there, well, I guess it says 0. We've used 0, but we'll find out today it doesn't matter what left endpoint you use. It's still antiderivative. Okay, so then, and that seems strange. I mean, you can have a different left endpoint, which would mean a different area. How is that still the same? How is that the antiderivative? But we'll get into that. But, so what we do is we just fix the left endpoint at a certain place, and then we let the right endpoint be our x. So, new right endpoint, new area. New right endpoint, new area. New right endpoint, new area. So we would graph our right endpoints as our x, and our area as our y, and that's our area graph. And that's what we were beginning to picture on Thursday, and we want to get more into that today. So the area function. So what we ended up saying is, okay, that would be like big F of x. Now let's talk about this notation a little bit. This x is the same as this x right here. So that means inside of here we have to have a different x. Now, so I was talking with a couple people. Let's pretend for a minute that our little f function, let's pretend that our little f function was 2x plus 1. Okay, let's just pretend for a minute that was our little f function. Anyway, I said, wait a minute, you used an x. You can't use an x. No, I can use an x there. That's fine. I can call it f of x equals 2x plus 1. I call it f of t. I can call it f of z, f of a, f of whatever, right? It's all the same function. It's a lump. But once I put it in here, with this x up here, then I would have to write it as what? 2t plus 1 or 2z plus 1 or 2r plus 1, something other than x. I could give you little f as this to start, but when it goes inside of the integral, it cannot be the same as that. Now somebody in the other class asked, could we, and so we could call that big F of x, like so. Now somebody in the other class asked, well, could you have a t up here and then x is in here? Sure. What would this function be called? Big F of t, right? And I've seen that happen before, and like on a sample test, a practice test, or a packet problem, or the final or something like that people get all freaked out. No, as long as this variable here matches this variable here. Okay, now again, another reason to tell you, or another way to see why these can't be the same. What if, and this gets to notation, and we'll get into this a little bit more today, what if I asked you then, what if I gave you this right here, okay, and said, find big F of 3. What have I just told you to do? Plug 3 in for x or t, and in this one that means the 3 would go there. In this one, 3 in for x means the 3 would go there. So what I'm asking you is this, right? Now, imagine if this was an x down here. What would I have to do? I had to put a 3 there too, right? So if this would have been an x, I put a 3 in here for this x, put a 3 in there, then I have to put a 3 in there, then that changes it completely, because then this would be the integral of 7, which is just a horizontal line, right? Which is a whole different thing. So maybe that helps to show why those are two different things. This value up here is the right edge. This value here is the input in the little left graph. They have to be two different things. Okay? All right. So, and then we actually could, I mean, this would, like, on our next quiz, which probably is going to be Friday, I believe, when we take our next quiz, I might ask you a problem like that. I'll give you this function here, say find f of 3. Well, for this particular one, you could graph 2t plus 1. You could go from 0 to 3. There'd be a trapezoid there, right? And you could calculate that area right there. Now, after today, you're going to find out that there is possibly another way that you can do that without doing the graph and so forth. The disadvantage to doing it that way is that only works if the graph gives you a geometric shape. If it's a curve, if little f is a curve, then all of a sudden that wouldn't work, right? So we're going to come up with, well, how do you think we're going to do it? Antiderivative, right? It's going to involve doing an antiderivative, right? Because that's what's going on there. All right, so let's take a look at this picture. No. This picture right here. Okay, so this is like what you guys had on your calculators on Thursday. We've got a little f function, which is the blue. We've got a yellow area inside of it, or underneath it, all right? And we want to picture in our head now the area function. If we were going to graph the area function, what that would be doing. So right now, my x, and we'll let the left edge be a, Okay, the left edge is A over here. And right now at X, I've got a piece of area. Now it doesn't even say here what that piece of area is. Let's say that piece of area is 1.5. So right now we would have an X coordinate right there, and we would plot 1.5, and that would be our area right now. It'd be positive area, correct? Now what happens as I slide the X to the right? What would that area graph be doing? Going up and getting less, because as I go to the right, I'm picking up chunks of positive area, but they're getting littler. The chunks are getting littler, so it's leveling off, concave down. Now, if we start thinking about the chart right away, now I kind of want to stay away from the chart line of thinking a little bit right now. I want to think area, but it's nice to compare it to the chart. In the chart, if little f is positive and decreasing, which is what it's doing right now, right? What should big F be doing? Let's take them one at a time. If little f is positive, what's big F? Increasing. If little f is decreasing, but what's big F? No. If little f is decreasing, what's big F doing? Concave down. So see how that matches with what we were just saying? Right? So somebody in our class said, well, we don't even need to think about area. Well, in a sense, we don't, right? Once we know that the area function is the antiderivative, then all that stuff in the chart about little f to big F or f prime to f is true, right? And so all those chart things should hold. But I really want to focus on how this area, how this area function works and talk about it in terms of not slope, but in terms of increasing and decreasing areas. All right, so here we go. So we're picking up positive area, so the area graph's going up. Now we're picking up what? And bigger chunks of negative area. So it's going down and going down steeper because the area we're picking up is negative, 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 more negative, until there. Now we're picking up what? Negative area in smaller chunks, right? So it's still going down, but it's starting to level off, right? So we're picking up negative area, so the area graph's still going down until here. Then it starts going up, which means we'd have a local minimum on our area graph. Sure enough, when little f is going from negative to positive in the chart, you've got a local minimum on big F, and that's what's happening. And now from here on out, we're going to pick up positive area, so the area graph's going to go up, up, up the whole time. Okay, so the area graph is like big F, which is what we said last time, antiderivative. Now, okay, on to the next one. So that makes sense. Now, here I've got a little simpler function. This is a function that we're going to work with and we're going to do a lot with here today. It's the function 3t plus 2, or I could have written that 3x plus 2. Up here I could have written it 3x plus 2, wouldn't have been a problem. But in here it's got to be a t. And we're going to do our left edge from some point A, so I don't know what A is, 8 right now, A's way over here, to x. So this is my area function. All right? So right now this dot right here, so we're going to take this another step. That dot right there is the area that I'm plotting. So x, see how it lines up with x. So my right edge is my input, and that orange area is the output. Right now it's negative. Would you agree? Negative area. Okay, now, as I slide to the right, what's happening? Picking up more negative area. So look what the dot's doing. It's going down. Going down, going down. I'm picking up negative area, until here. Now I'm picking up positive area. Picking up positive area, till there. Right? Okay, so now, so I do that. So we're picking up positive and it'll just keep going out of sight. Okay, and these are triangles, so we can actually find this area. Now I want to investigate this left endpoint here a little bit. What happens when it moves to somewhere else? That's the question. Don't answer. Now some of you might have a thought in your head already about what's going on. So hold that thought. When I move it somewhere else, because we've been keeping it over to the left and we've been moving to the right. Okay? What happens if I bring that point say in here. Okay? Now, let's bring x back over here. Okay? And I've got a little piece of positive area, and there's our dot again. So as I move to the right, no big deal, positive, 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 there it goes out of sight. Now let's bring it back the other way. Now, before we get into this, we got to remember, when we talk about a function increasing, what's a key element of that? That we're going from left to right. So when I look at this dot here, so this is something we got to be careful of. As I'm sliding this way, some people might say that that dot is going down. Well, yeah, but if you could picture the graph that dot is on, we would say that graph is increasing, right? It's going up. So we're going to be moving this way, which is opposite. So we got to be careful. When we talk about increasing and decreasing, we're always talking about going left to right. All right. So now, anyway, this is positive area. So what's happening here is as I slide past this, of course, what's my area right here? 0. Now let me slide past. That's now negative area, isn't it? And so look what the dot's doing. It's going down into the negative. That makes sense. And negative, negative, negative. Now I'm picking up positive, right? Positive, and so the graph's coming back up, right? Okay, so let's get it over to here. All right, so now my integral goes from a to x, which is backwards. So this area at the far edge is positive area. Everybody with me? Okay, now I'm going to talk about increasing, decreasing, because now I'm going to start going left to right. Before, when I was over here and I slid this thing, I was picking up orange area. You remember when A was over here? Hang on here a second. Let me switch to this one. Okay, when A is over. Okay, when A is over here, and I slide x to the right, okay, I've got some negative area, and I'm picking up negative area, picking up negative area, picking up negative area, picking up negative area. Negative and getting more negative, right? So what's the area graph doing? Going down, right? Negative getting more. Now I was picking up littler chunks, right? So it was leveling off, but it was negative. Picking up negative area. Now, let's come over to this other one, where I've switched. Wait a minute. Oh, yeah. Sorry. Forgot where I was at. Okay. Now the A's over here. Now again, I'm going to slide my X this way. But what is this area right here? This is positive area. As I slide my X, what's happening to the orange? Right, but I mean this. Yeah, I'm losing what?
Positive area.
Positive area. Now think about that. In the other one, when I was over here, I was gaining negative area. On this one, I'm losing positive area. Isn't that the same thing?
Yeah.
It's the same thing, right? So, and now why am I making a big deal about this? Because people tend to get too hung up with this left endpoint. When this left endpoint changes, they think that like changes everything. It changes a little bit, but it doesn't change much. Okay? So the area function is still doing the same thing it was before. It's just that when the left edge was way over to the left, as I moved this way, I was gaining negative area. Now what's happening is I'm losing positive area, which is really the same result. So look what happens. Here I'm losing positive area. Now what do we say this area is? Negative. So what's happening? I am losing negative area. Well, if you lose negative area, what happens to the area graph? It goes up. It increases because I'm losing negative area now. That's like gaining. So now what happens until the A? So same thing. I'm losing negative area, losing negative area, losing negative area until here. Now I'm gaining positive, but it's the same thing. You see that? So that area graph still did the same thing even though A was in a new place. All right. Now, let's move the A back here. Let's move the A back here. Okay? Now, let's talk about, let's get a little more specific with that left endpoint. All right, so let's say we had the integral from 0 to x of little f, and we had the integral from 1 to x of little f. All right, so tell me what you think about those two. Tell me what, Spencer, what were you saying? No, that's a good thought. Something about local max and min, but it's not. Doesn't have to do with the bottom number. That's right. It does not have to do with left input. Okay, a vertical shift or a horizontal shift. I see horizontal. I see where it comes from because one, the left edge is a 0, the other one is the right edge. But now we're talking about the area function, right? I mean, the picture of the area would shift. I agree with that. But remember, the area function is x coordinate and then the corresponding area that goes with it.
Time to pack up.
Your wife said the same minute. Something about, she gets everything. Makeup or something.
See, look, it's almost 2:45. It is time to pack up.
You bet.
All right. Yeah. Oh, yeah. Mr. Mark comes in.
Yeah, it's time to pack up.
Again, think about the area function. Let's do this before we talk more about what Brenna said here. If I had, okay, here's the integral from 0 to 1. And I can't really move that around while I'm in this mode, so let me just redraw it here. Okay? Well, let's pretend it's any function. Doesn't matter. So this is little f. Okay? So, and let's put x way out here. All right? And here is 1. So here we have the integral from 0 to x. Correct? And let's say that that is, for this particular x spot, let's say that's 18. And let's say, let's change color, and let's say that from 1 to x is the red, and let's say that's 10. Okay, would you buy that? Okay, from 0 to x is 18, so that's all the blue area. From 1 to x, let's say that's 10. Okay, so we would have two different area graphs here, right? Whatever this x coordinate is out here, let's say it's out here at 4. For this one, we'd have the point 4, 18, and for this one, we'd have the point 4, 10. Make sense? Okay, now let's move this x over 1. Let's move it to 5, let's say. Now, what just happened when we moved that x over 1? You gained some area. You gained the same amount of area to both. So let's say when we moved over 1, we added 3. We added an area of 3. Okay? So now we're at 21 and 13. And let's say we move over again. We add the same amount of area again. So I will say again, and maybe Brenna will see if she still thinks that way with her answer. The difference between those two area functions is what? Vertical shift, isn't it? Wouldn't those points always be how far apart?
3.
Well, no.
I guess
10 and 18, and then they each gain 3. And then if we move over, they each gain a little more. Or maybe if the area went negative, they would lose a little more. What's the only difference between these two area functions?
Vertical shift.
Well, yeah, the vertical shift, but in terms of the picture. This piece right here, this piece must be what? This piece is 8, right? I mean, if this whole thing's 18 and this is 10, this piece was 8, right? The only difference between the area function from 0 to x and the area function from 1 to x is that fixed piece of area between 0 and 1. That's the c. In the
I was gonna say that's C.
Right, because in our antiderivative, we've been talking about how the area functions in antiderivative. Remember, every antiderivative has a plus C in it, doesn't it? Okay? And so a new left endpoint just gives us a different C, which fits perfectly with what we talked about. Antiderivative's got to have a C. And the only difference between those two is that fixed piece of area, a constant. In this case, my example, an 8. Okay? So this, and I never get enough of seeing this. And I think this is really neat to see. Oh, this, yeah, there's C in this. I didn't even get that. All right, look. So let's graph this. I think I can do this real quick. I can graph this set of points. Okay, there is my area graph. It is a parabola. That doesn't surprise us either, right? Because little f is a line, so the antiderivative should be a parabola. Okay, so again, like we said, when we're over here, we're losing positive area, so it's going down. Now, actually right here we get 0 area, don't we? We're still losing positive area, so that makes our area go negative. Okay, we're losing area. Here we start losing negative area, so the thing comes back up. So notice, isn't this the key point right here? We were talking about the local minimum. The left edge doesn't matter, does it? The local minimum is still, but think about that. In the chart, the local minimum is when little f changes from negative to positive. And the blue graph's never going to change. When I move around my left-right endpoints, it doesn't matter. So watch what happens. I think this is awesome. You guys will see it. When I move this A, what's going to happen?
It's gonna be.
That's not going to stretch it.
It's shifting.
It's just shifting it up and down. Look at the local minimum. The local minimum is still at that place. First time I saw this with this program. All right.
Probably give you goosebumps.
All right. So, but that's it. Okay. So, summarize a little bit, and then we're going to get into the algebra. Because if you think about how we did derivatives, now this is a much more compressed schedule because we know so much more. But when we did derivatives, we did a whole bunch of graphical stuff. Same thing with areas. We've done some geometry. We've done some areas. Okay. Then we got into the algebraic part of it with the derivative rules. Well, that's what we're going to get into with the antiderivative stuff as well. Get into the algebraic part. Matter of fact, just something to file away here. Our next gateway test, our last gateway test
We have another
for
one of those?
antiderivatives. Absolutely, we got one for antiderivatives.
You're
Is
gonna be
probably in 2 weeks. Probably a couple weeks, or a week from this Friday, possibly, or somewhere in that neighborhood. Okay, so we're going to be getting into the antiderivative idea. Okay, so
It's usually past that.
left endpoint is the plus C. The area function as a whole is the antiderivative of the function inside the function you're doing the area under. So let's go to some problems we're going to work out here. If you would turn to page 320, I believe. Page 320, in our homework assignment today, there are 21, it says on there 21 through 28 we're going to do in class. And that's what we're going to work on right now. Then you're going to have some homework problems to do that are just like those. Now again, we're going to first do them graphically, and then we're going to talk about how we can do them using the antiderivative formula. You're going to do the same thing on your homework. There's going to be a couple that I'm going to want you to draw the pictures and do them graphically, but then on the others you'll be able to do antiderivatives if you need to on some other. Okay, so this is page 320, it's number 21. And they've given us this function. Now they put little f in here. I'm going to go ahead and write it in just to remind you that, okay, these should be t's. So I'm going to write them out this way. So what we've got here is we're trying to find formulas. Now we know about the plus C idea. We know about antiderivative. I still want to do this graphically, so it is a little more work. But I still think it's cool to see how this works out. Now, the downside to this is it's limited. It only works on ones where we have the geometry capabilities. But it is still good to see. So this is my picture. Let me get rid of some of this. Let's go to this Okay, so here I've got the function. So everybody, there's going to be three of them. We're going to graph the first two, big F and big G. Then we're going to do it a different way for H, and you're going to get to do the same thing on your homework. So I think you should draw this picture for 21 for big F. This is the function 3x plus 2. Okay, y-intercept of 2, slope of 3. We're going to do big F first, which is the integral from 0 to x. Okay, big F is the integral from 0 to x. In this homework problem on number 21, they say find the formulas for big F, big G, and big H. Okay, so we're going to do big F and big G strictly with graphs, and big H kind of that way, but we'll cheat a little bit. And then I'll show you how we can do them algebraically. So here's my picture. I've got my left endpoint at 0. I've got my x off to the right somewhere. Just draw your x off to the right somewhere. Shade yourself that area, which makes what shape? Trapezoid. So what I need here is a trapezoid area. So that would be 1/2 the sum of the parallel bases times the height. Now remember, this is a trapezoid on its end, so the height is actually down along the bottom. Okay, the parallel bases are actually the two sides going up. So one base would be over here, and one base is here on this right end. All right, now, here's our function, little f. So what's this left base over here? 2, and that's not going to change, right? But remember, x here will be sliding and moving. So what is the right base? Okay, it is 3x plus 2, right? Now let's think about this. How do we get this base? Well, technically the way we get, you could just look at the graph, but technically we put a 0 in for t. We get 2. How do we get this one? We put a x in for t. Now that's another place where it shows how this is a t in here, but when we work it out, we end up with x's in the problem because we put an x in for the t. So right here, this right edge, we take x, we plug it in for t, and we get a y value of 3x plus 2. Distance here. X minus a, in this case a is 0, so x minus 0 would just be x. All right, so let's simplify that. We have 1/2 x, inside the parentheses is 3x plus 4. We distribute that, we get 3/2 x squared plus 2x. Is that right? When I distribute? So I'm going to come back over here, and we said that was what? 3/2 x squared plus 2x. What do you notice? It's the antiderivative. Surprise. But yeah, there it is. Raise the power up 1 to a 2. Divide by the new power. That's our derivative, or antiderivative formula, right? Antiderivative 2 is 2x. And what about the c? In that one, the c was 0. Okay, and again, I like being able to do it. I like how, that was a trapezoid, where that came from. Remember one of our derivative rules was kind of cool about the fact that x cubed was 3x squared. Where did that come from? We just did the slope. Remember our long way? Limit as h approaches 0, f of x plus h, that whole thing. We worked that all out, factored, canceled, and all of a sudden, voila, at the end, we started with x cubed, we ended up with 3x squared, and it was all just from the slope formula. Same thing here. This was just the area of a trapezoid. And there came out antiderivative. Okay, let's go back to our picture, and let's change this. Let's do G now. What was big G? What was the left endpoint? 1. So let's slide our left. So redraw a new picture. Put your left edge at 1. Again, it's a trapezoid. Now remember, if little f was not a line here, we would be in trouble because we wouldn't be able to do the geometry formula here, and so that's why this is a little limiting, but it's nice to go through at least, you know, one time here, one time in your homework. Probably not going to have to do that on the quiz. Okay, so again, we have a trapezoid, so we're looking at 1/2 sum of the bases times the height. Okay, what's my left edge here? This is 1 now. This is x. So we put a 1 into the function, we get 5. We put an x into the function, we get 3x plus 2. Right? That's our left parallel base, our right parallel base of our trapezoid. Times the height, which is down here. That would be x minus 1. That is correct. That would be x minus 1 because the distance between here is those two subtracted. Okay? X minus 1. So let's see, we have a 1/2. We're going to have to FOIL this. We're going to have 3x plus 7. We're going to have x minus 1. There's no way this can come out right. We got a 1/2. We FOIL that. 3x squared. Outers 3x. Negative. Inners 7x. That'd be 4x. Minus 7. Distribute. 3/2 x squared plus 2x minus 7/2. Holy mackerel, look at that. There's the c, right? The c is negative 7/2. So now, so on the homework, I'm going to want you to do that. It's going to be similar, but just with a different little f function. But again, our graphical evidence was pretty convincing. When we shifted the left endpoint, it just shifted the area function up and down. When we talked about it as a fixed piece of areas, the only difference between these two is the area from 0 to 1. That seems pretty convincing. As a matter of fact, that probably tells us that what is this area right in here? What's this area right in here? That's got to be 7/2, right? The only difference between the first picture I drew, which started here, and this picture, the only difference between those two is this fixed piece of area, 7/2. So the first function was bigger, so it makes sense that my second picture had a minus 7/2 in it, right? Because the second graph, big G, is littler by that amount. Okay, so it makes sense that that was a minus 7/2 there, because I lost that piece of area that was 7/2. Now, we can do that same line of reasoning with this one, because we know this is going to be 3/2 x squared plus 2x. We just don't know what the c is. So let's go back to our picture, and you don't have to draw a new one if you don't want to. We'll just do it together up here. So let me slide that left edge over to -2, which is where it's supposed to be on this one. And now what have I gained from, let's go from the original big F. Yeah, I've gained this little piece and all this. Now, let's think about this. Is this positive or negative right here? Positive, because our left edge is over at A, so we're going that way, normal way, so that's positive, and then this area is negative. All right, so what's this? Well, it crosses at 2. That'd be 1/2 times 2 times, what's this? Oh, we got to find out where that crosses, don't we? How would we do that? That would be where little f is 0, which would be at -2/3, right? So this is going to be half the base times the height, so that would be 1/2, 2, those would cancel, so that's 2/3 right there. And then this area would be 1/2 times, how much would this be over here to -2? 1 1/3, right? Because we got 2/3 to there, so 1 1/3, that's 4/3. And then what's this down here? How would you get it? Put -2 into here, right? It'd be this y value, so put a -2 into there. That'd be -6 plus 4 is -4. So that's a height of 4. So 1/2 times, so that'd be 4/6. That's 2/3 times 4. That'd be 8/3. Is that right? Well, and it'd be negative, right? And that'd be negative. So add those two pieces together. -6/3 would be -2. Now let's think. We got to think about this with positive, negative. So how does this compare to the original function? I guess what I'm asking is it 2 less or 2 more than the original function? It's 2 less than the original function, because the original function was this piece of area. What we've added to it is this much, which is more negative than it is positive. So we've added -2 to the original function. So if we go back to what we had, here was our original. So the original, this new one's got to be 2 less than that, so it would be negative. It would be negative. And you'll see in a minute when I start talking about C how that affects, when we think about that area, whether it's positive or negative, we have to think about that C. Okay? All right. So, on your homework, there's going to be a similar problem. I'm going to tell you that big F and big G, you draw your graphs, do your area formula, and show that it comes out to be the antiderivative. And then on the third one, on H, you just do what we did there. Okay? Well, as a matter of fact, you can even do what I'm about to do right now. Because since we have an antiderivative formula, here's a whole other way we can look at this, algebraically. Okay? I would submit to you that this is really an initial value problem. What's an initial value problem? It has an initial condition. It's a problem with an initial value. We're missing something though. Differential equation. Initial value problem is a differential equation with an initial condition that you use to solve for the C. Think about that. That's what we're doing, is solving for a C. So there's got to be some connection here. It's why is this a differential equation? What's a differential equation? Equation with a derivative in it. Do we have an equation with a derivative in it? Little f. Little f is a derivative, right? This is technically a differential equation problem. The only thing I'm not sure about is the initial condition. Now, the initial condition is used to find C. Well, we were able to find C in every one of those. So there's got to be an initial condition in here, but it's kind of hidden. So what I want to do is this. Okay? I want to look at this. We'll start with big F up here. And I think it would be a good idea to write this down for yourselves as well. And since you knew this is little f in here, right? Right away we knew that this was little f, even if they hadn't given us this up here. Right? As soon as we wrote it as an area function, like what I have on the board over here, as soon as we write that area function, whatever function is inside of that integral, that's your little f. Okay? And so the area function, the integral symbol, turns it into antiderivative then. So we know that big F here is going to be 3/2 x squared plus 2x plus c. We just know that. Now, here's another place where we're still going to have people mess this up. If I wouldn't have given you this up here, if I just gave you this, and you said, oh yeah, that's antiderivative of this that's in here, and when you do your antiderivative, some of you are going to keep t there. No, when you do the antiderivative, it's x that goes in there. Think back to the area thing we did, where the x was on the right edge of that trapezoid. We plugged the x in for the t. You end up with x in it, not t's. Okay, so you do your antiderivative, but you write it with x's. Okay, now, we need an initial condition. What that means is we need some value of f that we know, big F. Is there any value of big F that we know? Do we know big F of 0? Now remember on this page, when I told you when you're trying to find big F of 3, what's that mean? You put a 3 in right there. So big F of 0 would mean we put a 0 right there. What's the area from 0 to 0? 0, that's right. So whenever you know the left endpoint, you know at least one area. You know the area that when you go from 0 to 0, that there's not going to be any area. So look what happens when you stick that 0 into here. You get 0 plus C equals 0. C equals 0. Sure enough, that's what we have. So look what we could have done on G. On G, we know that the antiderivative is 3/2 x squared plus 2x plus C. And we also know that G of 1 is 0. Because if I put a 1 right here for this x, that means I put a 1 right there for that x. The area from 1 to 1, 0. So we know that. So there's an initial condition in there, but it was kind of hidden. All right, now what do? We put a 1 in for x. So we get 3/2 plus 2 plus C equals, just like we did with differential equations and finding our C value. So what's 3/2? 1.5 plus 2 is 3.5. That's 7/2. Oh, this is going to work out nice. 7/2 plus C equals 0. C equals -7/2. So, if the nice part about this is if we get a little f function that we can't do an area, we can't do a geometric shape, no problem. As long as we do an antiderivative, we can do it this way, and we can find that C. And then, of course, on this last one, we're not sure. We think that was supposed to be -2. We know that h of -2 would be 0. So if I put a -2 in here, -2 squared is 4 times 3, that'd be 12/2, that's 6. -2 times 2 is -4, plus C would have to equal 0. 2 plus C equals 0. Sure enough, C would equal -2, and that's what it is. So, on the homework, when we get a problem, when you get the one that's like this, like number 21, and all we've done is 21 so far, by the way. When we get to the one that you're going to do that's like 21, the first two I want you to draw graphs, do the area like trapezoids or triangles, whatever they are. The third one you can just do this way, okay? And I think there's at least one other one. I think the very first problem in the homework is this kind of thing, where you do an antiderivative, find the C value, basically. Okay? Now, let's go on to, I wanted to do 21 through 28. So let's talk about a few more of those then. Okay? And again, a lot of this now is just notation. A lot of this is just notation. The overriding theme, antiderivative. The area function's antiderivative. We also, another big point is the left endpoint determines the C. We can get it by graphing and doing areas. We can also get it by doing an antiderivative and doing that initial condition thing that we just saw there. We also have, and these are other problems that are going to be your homework. We're going to get to them here in a second. There's going to be problems that just have to do with chart kinds of questions. Where is big F increasing? Where is big F concave down? You can answer them using the chart, but I'd like you to think of them in terms of areas. You know, why is this increasing? Well, because you're gaining positive area. You know, we would have used to say when little f's positive, big F's increasing. Now I would like it to be, well, in this particular problem, big F's increasing because you're gaining positive area. See the difference? So those are some of the things we're talking about needing to do. All right, 22. 22 says find C. So this is just some stuff with notation, but I want to make sure we're comfortable with it. So it says find G, or find C such that this is a true statement. Now I want you to get comfortable with this. You're going to see this a lot. What this is saying is that big G and big F are the same, except for some constant. They differ only by a constant. Well, that's what antiderivatives, that's what we talk about with antiderivatives. So basically this is saying big G and big F are both antiderivatives of the same function. Now we know that, right? The little f that we just found. But now what's C? Well, when you look at it, what's -7/2, right? But it's not. Positive 7/2.
Oh, yeah.
Okay? And so when you get these, you just have to think, okay, now, wait, why is it positive, why is it negative? There's a couple ways you could do it. One way would you think, okay, this is saying F plus something makes G. So if I look at F, oh, wait. Oh, it is negative. It is negative in this. I'm sorry. I'm thinking of another one here. Yeah, so you would look at this and you'd say F plus something makes G. Well, F plus what would make G? Oh, plus negative 7/2. I guess what I was thinking, I did this one in the other class. I said, what if it would be this way? Because they just as easily could have given you this question, right? So now this one is G plus what makes F? Well, G plus what would make F? Well, you'd have to get something to cancel this out. So it would be a positive 7/2 that would make that. Okay? Another way that these are sometimes written is like number 23. 23 says, find big F minus big H. Well, if you think about it, what should that be? It should just be the constant, right? It should just be the constant. In other words, if these two antiderivatives differ only by a constant, when you subtract them, you should get the constant. But is it positive or negative? That's the key. In this one, it is positive. Because if you take, what order was it? F. So if you take F minus H, 3 x squared will subtract out, the 2x's will subtract out, and then you have 0 minus negative 2. So it'll end up being positive 2 is your answer there. Okay? But again, that's just another way of saying that big F and big H are the same except for a constant. They differ only by a constant. All right? So just some notation there. All right, 24. Now we get into the chart kind of stuff, and this goes really fast. Where is big F increasing? When little f is positive. Right? So that'd be from negative 2/3 to infinity. Now I know I just got done saying that I want you to say things like, well, that's where the area you're gaining positive area. Not in this particular section. In this particular group, I'm not as worried about that. But you'll see when you get into the other part of your assignment, it'll make more sense to you. To talk about areas as much as you can. As much as you can. Okay, where is big F or big whatever decreasing? Negative infinity to negative 2/3, right? And that's where F is negative. Little f is negative. Again, that's just chart kind of stuff. All right, and then it talks about concave up. 26, is F concave up anywhere? When is big F concave up? That was big F. Right? When little f is increasing, which is always, right? And if you go back to the picture that we had up here, it was always concave up. It was a parabola like this, because this graph's always increasing, so this was always concave up. But for different reasons. Remember, when we had the x over here, we were gaining negative area, but littler chunks of negative area. So it was negative, but getting less negative. And then we started gaining positive chunks, so it was positive and more positive. And so it was concave up, but for two different reasons. And then concave down would be never. So is that 28? Or 27. Concave down would be never. And then, of course, this, see now, in the book, 28 was supposed to be the big reveal here. Right? 28 says, oh, are big F, big G, and big H all antiderivatives? Well, of course they are. Yeah. So, right, and you're then supposed to realize that they were. So, yeah, oh, very good. Good. So there we go. So that's pretty much it. I mean, with the notation, now if you get your that's about right. That's about right. So if you yes, too much time. I've got to talk to you. If you get your homework sheet out, okay, we're going to do. No, that actually works just fine because you'll be able you'll get enough of it done to, especially the early parts of it, to be able to work and to ask questions and so forth. So what we just did on this screen here, if you look at your assignment sheet, so what we just did with all of this, okay, is pretty much what you're going to do. Is pretty much what you're going to do with 29 through 36. So if you look at the 5-2 line, just the one line, not the one that says day 2, Okay, just the 5-2 line. We did 21 through 28 there. 21's the one that took all the time. You're gonna do 29 through 36, which is the same thing but with different functions. A different little f. So on 29 will be where all the work is. Now you'll be doing a big F, big G, big H, just like that. On big F and big G, I want you to draw the picture of little f. I want you to draw in your trapezoid triangle, whatever it is, shade it in. I want you to do that area, work that out. That's what I'll be looking for when I come around looking home. Okay? Now on the big H, you can do, just kind of how we did here with the antiderivative, find the C that way, that'll be fun. Okay? But I think you should save that for later, come back to that, because you already know how to do that, and that's probably not going to give you that much good. I would start with number 2. Now I'm trying to think why I didn't just say 2 through 14, but I think they're different sections. Number 2 is a problem, then 3 through 8 is a group of problems, and 9 through 14 is a group of problems. So I think that's why I did that. But I think those would be good ones to do first here during class time, because some questions may pop up that I might be able to help with, so you might be able to. Make sense? Everybody know what line we're on? And 5.2, 5.2. Just the 5.2 line, not the day 2 line. Okay? Oops.